Hi, and here we will continue doing problems related to fluid mechanics using this book. In this problem 2.28, we have a U-tube manometer, which is this one, is connected to a closed tank containing air and water as shown. So this is our closed tank that contains water and air. At the end of the manometer, right here where we have the closed valve, the air pressure is 16 psi 8. 16 psi stands for pound force per inch squared or square inch. The A stands for absolute. Determine the reading on the pressure gauge for a differential reading of 4 feet. So this is called the gauge fluid. So this is the fluid that we use to gauge the pressure inside the tank that contains water and air. Express your answer in psi gauge. Assume standard atmospheric pressure and neglect the weight of air column in the manometer. So here we are asked to determine the reading on the pressure gauge, and they are referring to this right here. This is the pressure gauge. So this is the goal. We want to know how much pressure at this point. So we want to know the pressure along this horizontal level of water right here. So first let's take a look at this. So here our final answer should be in gauge. In this setup, we are told that we have air that is applying a pressure on the gauge fluid for an amount of 16 psi absolute. Imagine that you have the same gauge but here at the top. The question, this gauge will read how much pressure in here, and that's what we want to find. And remember, we are told that we can assume standard atmospheric pressure. Now, a standard atmospheric pressure is 14.7 pound force per inch squared, and you can find this in any reference table. A pressure gauge, what is the pressure gauge? Pressure gauge is the difference between the absolute pressure minus the atmospheric pressure. So if you imagine right here where the red cursor is at, we have a pressure gauge like this one where it's connected to the closed tank. We want to know how much this pressure gauge will read. So in here, we will replace the pressure absolute is given to us as 16, which is pound force per inch squared. That's the absolute. Minus, we assumed a standard atmospheric pressure, which is 14.7 pound force per inch squared. So 16 minus 14.7 will give you 1.3 pound force per inch squared. And remember that, in this problem, we have the height in here in feet, and the given gauge fluid specific weight is also expressed in feet cubed. So we can convert this from inch squared to feet. And as you know, 12 inches is equivalent to 1 feet. So inch squared will cancel with inch squared and it will give you feet squared. So we will multiply 1.3 times 12 to the power 2 or 144. So here we were able to convert the air pressure from absolute to gauge. So now our goal is we want to find the pressure at this point. So let's write here. So let's start and write pressure gauge, because that's what we want to find. Now, when you multiply, so we what we will do is we will go all the way to the other side of the setup, and we will start all the way at the end. So here we have the 1.3 psig. But remember, we multiply this by 144, it will give us 187.2 pound force per feet squared plus. Now, as we increase in depth, the pressure increase. So that is why we have positive. And from hydrostatic formula or equation for a fluid, for a static fluid, is the specific weight of the fluid times the height, which start from here to here. So that's the portion. So here we will write down 90 pound force over feet cube times the height of 4 feet. Then we will continue for the water column. We are increasing in depth, so that will be positive. Why? So that will be positive. The specific weight of water, you can find it from any reference table, is 62.4 pound force per feet cube times the height of 2 feet. So let's plug this into our calculator. So 187.2 plus 90 times 4 plus 62.4 times 2 feet. It will give us 672. So the pressure gauge is 672 per feet squared. Now we are asked in this problem to express it in psi gauge. So this is a gauge reading. So we will use a conversion factor. So in here we know that 1 feet is equivalent to 12 inch, and we will square this. So that means we will divide this by 12 squared, so divided by 144, which will give us an answer of 4.67 psi g, and g here stands for gauge. So here we have problem 2.29, a closed cylindrical tank, which is this one right here, filled with water and has a hemispherical dome and is connected to an inverted piping system as shown. So this is the inverted pipe. The liquid in the top part of the piping system has a specific gravity of 0.8, which is this one. This is called the gauge fluid. And the remaining part of the system are filled with water. If the pressure gauge reading at A, right here, is 60 kilopascal or 60,000 pascal, determine A, the pressure in pipe B, right here, and the pressure head in millimeter of mercury at the top of the dome, which is right here. Now, here the pressure reading is 60 kilopascal, right? And remember, the pressure in a horizontal plane is the same. So here is 60 kilopascal, here is 60 kilopascal, here is 60 kilopascal, here is also 60 kilopascal, and here is also 0 kilopascal. And remember, our goal is to find the pressure at B and the pressure at C. Now let's step back a little bit and discuss some important concepts as a practice solving this problem. So this equation is the fundamental equation for fluids at rest and can be used to determine how pressure changes with elevation. Now, since the specific weight is equal to product of fluid density and acceleration of gravity, which is this one right here, changes in specific weight are caused by either the density or gravity. Now, for most engineering applications, the variation in gravity is negligible. So our main concern is with the possible variation in fluid density. In general, a fluid with a constant density is called incompressible fluid. So this is what we are dealing with in here. The water, the gauge fluid, these are called incompressible fluids. Why? Because their change in density is very negligible, meaning that um, the density of water as we increase in depth doesn't change that much. It's very small. So that's why we can consider that fluid have a constant constant density. And when we say constant density, we mean incompressible fluids. So for liquids, the variation in density is usually negligible, even over large vertical distances, so that the assumption of constant specific weight when dealing with liquid is a good one. Finally, what I want you to, a very important concept in fluid statics, the pressure must increase with depth. Why? Because to hold up the fluid above it. All right, so now let's start solving the problem. So here we are told that we want to solve for the pressure at B. So now let's write the pressure at B here. Now let's go all the way to the other side of the setup and all the way at the end at point C. Now here we have a pressure, we have a gauge that read the pressure. So this pressure right here reads the pressure along this horizontal dashed line. So it tells us how much pressure is being built up from this hemispherical shape. So that tells us that the pressure in here is the same and the pressure in here is the same. So we can start solving for pressure at B from pressure at A. Next, now we are working toward the pressure at B. So now we are increasing in depth. So that means positive. So we want to find the pressure at this point. So the pressure at this point will be what? Will be the specific weight of this gauge fluid times the height, which is 3 meters. And that's what we're going to have in here, the specific weight of the gauge fluid times 3. Next, we want to go and find the pressure in here. And the pressure in changes vertically, but the same horizontally. So the pressure in here will be the same as here. And the difference in elevation will be 2 meters. So and because we are increasing in depth, it will be positive, the specific weight of water times 2 meters. All right, so now we want to know what is the specific weight for the gauge fluid. Here on the side, let's another concept called specific gravity, which is a ratio between the specific weight of the fluid divided by the specific weight of water. The specific gravity is given to us in the problem as 0.8. So now we can solve for the specific weight for the gauge fluid by taking the specific weight of water from one side of the equation from division to multiplication. And that's what we're going to have in here. So now let's plug in the values into this equation to find the pressure of the water in pipe B. So the pressure at A is given to us as 60,000 Pascal. The specific weight for the gauge fluid, we found it from this equation, which is 0.8. And the specific weight of water, you can either find it from a table or you can conclude it that, specific weight is gravity times density. And the density of water is 1,000 kilogram per meter cube times the gravity, 9.81, which will give you 9,810. Times the height of 3 meters, plus the specific weight of water, also something that you can find online, or you can find it from reference table, 98110 Newton meter cube times 2 meter. All right, so let's find out what is the this one here. So 60,123 plus 0.8 times 9810 times 3 plus 9810 times 2. So it will give us 103,164, and we want to find it in kilopascal, so divide this by 1,000. It will give us 103.164. And here is the pressure at point B. We found it. All right, so next what we want to do is we want to find the pressure at point C. And as you can see, the pressure at point C is what? Is the difference between the pressure at point A and the pressure at point C. So here you will ask me a question. When we solved for the pressure at B, right here, where my red cursor is at, we went all the way to the other side of the setup and started at C and concluded that the pressure at B reads the height of this fluid. And then we worked our way to pressure at B. Why don't we do the same thing and start at pressure at B, which what we found is 103.164, and walk our way back to pressure at C? Can we do that? Yes, you can. And matter of fact, you can use this as a practice. And what you can do is, or I can use my calculator and just to see if starting from pressure at A makes sense. So we said that the pressure at B is what? Is 103.164. Then we will go up. So as we decrease in depth, it will be minus sign. The specific weight of water is 9810 times. It's going up 2 meter times 2. Next, we will go up. We will decrease in depth. And so that will be another negative sign. And the specific weight in here is 0.8 times 9810 times, and it's going up 3 meter. And the pressure in here is the same as the pressure in here. So far, I should get 60,000 equal, yes. So when I did this, I get 60,000. So that's why I can start to solve for BC. I can start from the pressure at A. So right here, we will write down 60,000 Pascal. And as we decrease in depth, so that will be minus. And then we will use the hydrostatic formula, which is the specific weight of water times the height of 3 meter. So it will be 60,000 minus 9810 times 3. It will be 30,570 Pascal. And that's what we have in here. But remember, here we are asked to find the head pressure at point C in millimeter mercury. So just by rearranging the hydrostatic equation, because remember, hydrostatic equation is what? Pressure equal to the specific weight times the height. So here what we did is we solved for the height at C. And we found the pressure at C. What we can do, instead of water, we can change it to mercury. So we can find the head pressure in mercury. So let's plug in the values. And so this one will be divided by 133. It will give us 0.229, or I can round it to 0.23 meter. And as you know, 1,000 millimeter is equivalent to a meter. So we will multiply this by 1,000. It will give us 230 millimeter. That will be all. Thank you very much. Have a good day.